Okay, another thing, particularly today, might be of interest. Terminal velocity of raindrops falling through air. Not a human, obviously, but still falling through roughly the same fluid. Do you experience in your daily lives the impact of raindrops at 120 plus miles per hour? Yes? No?
Yes.
Yes?
No.
Wow. What planet are you living on? Okay, do you think it's less than or more than the terminal velocity of a human?
Less than.
Less than. Okay, when you step outside of class, look at the terminal velocity of raindrops. It's a few meters per second, just to mix up units, okay? All right, so, silly example, but kind of fun, is two fluids, two more or less identical steel spheres. Okay, this is amazing. The water quality in this building is something we're often surprised about. Okay, that's out of the faucet. So this is going to be a slightly not visible demonstration, but try and do it at the side. Okay, let's go here. Okay, steel ball falling through water. Okay, just watch what happens to the extent that you can see it. So, pretty fast, okay, still accelerating pretty quickly. You guys are the best. Okay, corn syrup.
Like that's an old thing.
This is a really long demonstration, okay? You can watch it till the end of class in principle, but we're not going to. Looks like they don't take them out of here anymore. There's like 8 other ones. All right, so terminal velocity. Obviously depends on the fluid density. But this coefficient C has a lot to do with viscosity as well. Viscosity, friction, those are very much related. It certainly isn't the case that this is orders of magnitude more dense than water, and yet the terminal velocity is reached essentially immediately, and it's extremely small. So this is an example of a very high coefficient, drag coefficient fluid. Yes, sir?
So the V in the equation, is it always terminal velocity?
So,
VD.
in the one that's in the middle chalkboard, no, this is the instantaneous velocity, and
Okay.
that's the instantaneous force. So I could write this as explicitly dependent on velocity, and probably I should have done, or dependent on time, but certainly dependent on velocity. In this case, it's very much the terminal velocity based on their equal and opposite. So yes, this should be, if I was being a little more clear, velocity. Yeah.
What is that liquid?
Corn syrup.
Oh, yum.
Yeah. Right.
Corn syrup.
So, just so you know what corn syrup is like. Okay, good. So, for now, that's all we're going to talk about drag forces. If necessary, I'll give you the explicit form of the force. You may be worried about terminal velocities. Take a look in the notes that I post for those of you who are interested in how to solve the equation, Newton's law equation, with a velocity-dependent force in it. You can do it. I'm not going to ask you to, I don't think, in this course, but you can do it. So if you're interested, take a look at it. All right, so for the remaining 10 minutes, I want to turn our attention back to circular motion and the dynamics, which means the forces associated with circular motion. So we've explored this one already. Quick reminder. All on the end of a string, uniform circular motion, at least for now. So the force that's allowing this to be accelerated in a circle is provided by the string tension. Okay, you guys already told me this last week. So there are of course other types of circular motion where the force is provided by another type of physical force. You'll remember me urging you not to use the phrase centripetal force. I don't like it. it suggests it's a new type of physical force, which it never is. Centripetal is a representation of an effect from another type of physical force. So, what other things may we be interested in? I think we talked last time when we did that about gravitation, gravity providing the possibility for circular motion. Of course, when we look at planetary motions in our solar system, that's where the force comes from. So the moon is in a pretty close to circular orbit because of the gravitational force exerted on it by the Earth. The Earth is in a more or less circular orbit due to the gravitational force exerted on it by the sun. Okay? So gravity is one clear example of where we can see another source for forces providing centripetal acceleration. Now I want to look at the case of, more mundane case of motions of vehicles around banked curves. It's a common scenario where we need to worry about circular motions. And the same will apply to aircraft turning in circular paths. The origin of the force is slightly different. So, what do I want to call this? The dynamics of circular motion. Continued. Okay, it's supposed to say continued. All right, what am I talking about here? You guys, when you drive on highways, relatively elevated speeds, when you approach curves, you'll often experience and see that the roads are banked. Okay, so they're not remaining horizontal; they are banked. So here's the case of a car, and in a moment, an airplane. Okay, this is always a little bit hard for me to draw in an unambiguous way. I want you to imagine you're driving this way, and then you're going to turn to the left. Okay, so the surface, road surface that formerly was horizontal gets banked in this direction, and then you're heading in a sort of circular path, so you're turning to the left. But I want to draw the vehicle like you're seeing it from behind. Okay, so here's the wheels, we're seeing it from behind. All right. Same thing over here. Now with an airplane. Okay, that's an airplane. Turning to the left. There's the engines. And the question is, how do we identify the force that allows the circular motion to happen? Let's say we're going to turn around in circles that are of fixed radius. What I want you to think of here is you're kind of moving around a center of a circle, which is obviously to the left. So you're heading around here horizontally around a circle that has its center here. I could, in principle, draw something similar over there. So this is the center of the circle in each case. All right. So the question is, what is it that provides the explicit force that's going to allow us to move in a circle horizontally? Because we know we need an acceleration. And we know in each case that we need an acceleration, which is the centripetal acceleration. So what is it that provides the force that allows us to do that? Yeah?
The horizontal component of gravity.
I know you're on the right track, but just rethink the words you just said.
The gravitational force.
So,
I guess it could be friction.
Here, if I was to ask you to draw the force strength gravity, how would you draw it?
Just straight down.
Okay.
Oh, so the normal force.
Okay, much better. So, the horizontal component of the normal force, nice. Okay, normal force, a little bit more complicated situation, but the surface of contact is this inclined plane. As always, we expect a normal force to be perpendicular to the surface of contact. So indeed, the normal force here is at an angle. Let me ask you, because it's kind of an interesting question, are there any other forces you can identify acting on this car? Let's see, what have we not had yet? Yes, sir.
There's a friction force.
Friction, interesting. So friction in this case is kind of a particularly interesting force to worry about. If the car is accelerating, by which I mean its speed is changing, then yes, there needs to be friction in the normal way. We'll be talking about friction with contact with rolling wheels. Let me say, imagine this was a icy banked road. So much so that in fact there was no friction between the car tires and the road surface. The question I'm going to ask you is to imagine that and answer the question whether it's still possible for this car to go around this banked curve without flying off the top of it. And it turns out that there's a certain orientation of this where it can, it's true. So in general, yes, friction. A little bit complicated. We're going to come back and explore that maybe in Thursday's class, but I'm going to work through an example of that with you. What about this case? We're looking at something which is very much analogous. We haven't, though somebody mentioned it last week, we haven't explicitly talked about the force which may be relevant for aircraft staying in the air. What's the force that we'll usually identify with an aircraft? Lift. Okay, lift itself, again, complicated, has to do with fluid flow around airplane wings. It's way more complicated than anyone ever tells you it is. It's not just due to the Bernoulli effect we'll talk about in a few weeks, more complicated. But the end result is that lift is a force that gives, that provides a force that is perpendicular to the plane of the wings, okay? So in this respect, the two phenomena look very much the same. And indeed, okay, there's a little bit of friction here. It's really a drag force in this case, as there is in that one, if it's moving through a fluid. We're getting much more complicated, as you see at this point, but in these simple extrapolations, what we can identify is that in fact it is the horizontal component of either normal force, so I'm going to write this as N horizontal, or L horizontal. It is that component which provides the force that's going to allow us to have this centripetal acceleration. Okay? So again, there's no new force beyond ones that we've talked about previously. It's an identifiable physical force, and in this case, it's the component of the force that acts towards the center of the circle. Before I misaligned it. The component of the force acting towards the center of the circle that provides the centripetal acceleration. So it's important to recognize that, and again, I think what I'm going to do is work a problem on that at the start of next class. Yes, I am, because we are out of time. All right, just one other thing I forgot to mention while I was writing up FYIs on the coursework. I posted a sample person exam on coursework. If you want to start taking a look at it, I'll say more about the exam on Thursday. Okay, go outside and look at the terminal velocity of raindrops.
Thank you.
On Thursday, the person whose water cup I have, feel free to come and grab it.
Class. And I have another class. My business was 3. Yeah, so I have
Does your roommate like talk about random stuff before Yeah, that's good. I mean, we have the same 6 Yeah. Yeah, I like to do like 2, and then it's like computer design. And like, yeah, I don't really know like 2, but I'll go back to like mental health.
no,
Yeah.